Alright, so in this video, we're going to prove the quadratic formula. So as you can see here, we have the equation ax squared plus bx plus c equals 0. Now, this equation can represent any quadratic equation in existence because we can choose a, b, and c to be any number we like. For instance, this could be 5x squared plus 6x plus 3 equals 0. And to solve for x, you're probably thinking to yourself, well, just use the quadratic formula, right? But where does it come from? That's our goal in this video. Now, one important thing to note before we get into this proof is that a cannot equal 0. And think about why this makes sense. Because if a was 0, then we would have 0x squared plus bx plus c. The x squared would go away, and it would no longer be a quadratic equation. So we have to apply the condition that a is non-zero so that we actually do have a quadratic equation, right? That's the only thing. So now let's get into proving the quadratic formula. We're going to start out by multiplying 4a on both sides of the equation. Just like this. And it might seem a little weird, like, why are we randomly multiplying both sides of the equation by 4a? Why not 3a? Like, what's the purpose? Where is this going to lead us to? Well, don't worry about that. It doesn't matter. We know we're allowed to do it because, for instance, if a equals, let's say, 3, then we're multiplying 12 on both sides of the equation, which is perfectly legal. We're allowed to do that if we want to. So let's just accept it and see what happens. Now, on the right side of the equation, we know that this is just going to be 0. But on the left side of the equation, we're going to have to distribute the 4a across. And if we do that, we will get this. Now, the next thing that I'm going to do is I'm going to subtract 4ac on both sides of the equation. And if we do that, this will go away. So on the right side of the equation, we have negative 4ac. But on the left side of the equation, we have this plus this. Right? Just like that. Now the next thing we're going to do is we're going to add b squared on both sides of the equation. Again, it might seem a little weird because it's like, why are we randomly adding b squared on both sides of the equation? Why not just b? Why not add b cubed on both sides of the equation, right? What's the purpose? Again, let's just accept it and see where it leads us. So on the right side of the equation, we have b squared minus 4ac. And on the left side of the equation, we have this plus this plus this. Now, for this next step, again, it's like, why in the world are we doing it? But it makes perfect sense. We are allowed to re-express 4abx as 2abx plus 2abx. Right? We know for a fact that this is equal to this plus this. All we're doing here is combining like terms. So if we want to re-express this as 2abx plus 2abx, it's perfectly fine. And so all we've done is we've re-expressed this 4abx as 2abx plus 2abx. That's it. So then, where is this all leading us to? This is the step where you may start to sort of see it. Check this out. What we're going to do is we're going to pull out the greatest common factor from the first two terms. If you observe this, the greatest common factor is 2ax. And if we factor out a 2ax from these two terms, inside the parentheses, you're going to be left with 2ax plus b. And you could verify by distributing across that this is equal to this. Now let's focus on our second group of terms. If we take out a greatest common factor from these two terms, the greatest common factor is b. And if you factor out a b from these two terms, inside the parentheses, you're going to be left with 2ax plus b. And again, you could verify by distributing across that this is in fact equal to this. And so at this point, we have re-expressed the left side of the equation as this. So this is all equal to what we have on the right side of the equation, b squared minus 4ac. So now that we're at this point, I'm going to take this and I'm going to rewrite it up at the top right here. So at this point, I've rewritten exactly what I have here, right here. But here's what's really cool. Notice that overall we have something times something plus something times something. And it turns out, just so it's clear to everyone what I'm about to do, I can relabel 2ax plus b as some number m, right? So I'm going to also rename this m as well. What that means is if I replace 2ax plus b with m, 2ax plus b with m, I will get this. And the thing is, I can factor out an m from these two terms. But in the parentheses, notice I'm going to be left with 2ax plus b. And again, you can verify if you distribute this across, it's exactly what we have above. Right, so this is all equal to b squared minus 4ac. Since this is also an m, we are left with m times m, or m squared. So m squared is equal to b squared minus 4ac. The next thing I'm going to do is I'm going to take the square root of both sides. Now, the square and the square root cancel out, and we get a plus or minus, if you recall. So if we do this, we have at this point solved for m. M is equal to plus or minus the square root of b squared minus 4ac. And we can re-express m as what it is, right? M is just 2ax plus b. And so at this point, it's really easy to solve for x. All we got to do is subtract b to the other side, then divide 2a to the other side. We'll start by subtracting b on both sides. And next we'll divide 2a on both sides. And we don't have to worry about whether or not a is 0 because we already stated at the beginning that a can't be 0. And so now we have solved for x, right? We have solved for x given this equation. So it turns out, given this equation, no matter what a, b, and c are, we figure out that x is equal to the thing that we have in the quadratic formula. So this is the whole idea of where the quadratic formula comes from. And so, yeah, it's pretty interesting how we can arrive at this, right? So yeah, that's pretty much it for this video.